Right, so today is the third class, radiation measurement. And today Joe Ross will be leading the class, and I'll be helping. And we have some terms which we're printing out, and we'll be able to give to you. And oh, this is better. This is backwards. So, how about if we start with showing this video?
Yeah.
Right? We found a good video from something called the Fuse School, which is an open source education site. And this is what our radioactive isotopes.
The identity and chemical properties of any atom are determined by the numbers of protons in its nucleus. As atoms get bigger and heavier, the nuclei get bigger and heavier, and the protons need a sort of nuclear glue to help hold them together. Neutrons provide this glue and prevent the positive charges of protons from repelling each other, thanks to something called the strong nuclear force. Elements can exist with slightly different numbers of neutrons, and we call them isotopes of an element. It is particularly common for heavy elements where a lot of neutrons are required to hold the nucleus together, but smaller and lighter examples include the isotopes of hydrogen. Hydrogen-1, hydrogen-2, also called deuterium, and hydrogen-3, also known as tritium, are the three isotopes of hydrogen. They have 0, 1, and 2 neutrons respectively. Tritium is the heaviest isotope of hydrogen, as it has a larger mass number. Note that in each of these isotopes there is a single proton. This means that the element is unchanged, and that's an important point. It is still hydrogen and will react chemically in exactly the same way. There is often more than one stable isotope of an element. In fact, look at the world around us is made up of stable isotopes. However, sometimes there aren't enough neutrons in the nucleus, or there may be too many for it to be stable. An analogy is a cursor carrying boxes. If you try to carry too many boxes, you'll end up dropping some. And if you continue, you'll keep dropping boxes until you reach a manageable amount. This is your stable state. And nuclei behave in a similar way. They will try to stabilize themselves. If there are too many protons or too many neutrons, the nucleus can spontaneously rearrange itself and throw out particles in the process. This is essentially what happens in radioactive decay. Isotopes that have unstable nuclei like this are known as radioactive isotopes or radioisotopes. In our hydrogen examples, both deuterium and tritium are unstable and are hence radioisotopes of hydrogen. The more unstable the nucleus, the faster it will try to rearrange itself into a more stable state. And another name for this process is radioactive decay. Radioisotopes are often used in medicine to trace aspects of body chemistry or blood flow. For example, a small amount of the radioisotope technetium-99 may be injected into the bloodstream to show up on medical imaging and X-rays. This is known as a medical tracer. Tracers can be used by chemists to understand how a reaction works. Atoms of radioisotopes can act as markers, allowing chemists to follow how a reaction sequence occurs. And of course, radioisotopes are also used in radiotherapy to kill malignant cancer cells. So, as you can see, isotopes are important in modern science, and so we'll finish with a summary of the key points. Isotopes of the same element have the same chemical properties. Some isotopes are stable. Isotopes that are unstable are radioactive. Radioactive isotopes are also known as radioisotopes. Radioisotopes can be used as tracers or markers in chemistry and medicine, and they are also used to kill cancer cells.
Okay. So that's just a short introduction. Some of the concepts that Joe's going to be explaining more.
You had a question. We were talking about what is alphas versus betas. Well, we'll back up a little bit. And what is ionizing radiation? Because there's
Some terms. Will be
pretty new thing. A lot of these terms have different definitions or slightly different uses in different areas of science. You know, and very generally speaking, radiation is anything that is emitted and moves from one place to another. So we can talk about even volatile chemicals, essentially paint drying, that the volatile comes out that radiates it. But if you get to this discussion, and most cases now, when we say radiation, we mean things that move by atomic processes, subatomic particles, photons, or subatomic particles or photons. Okay, subatomic particles are going to be neutrons, electrons, protons. And because of the nature of physics and the nature of the universe, they tend to group in certain ways. The most common radioactive carrier is a photon. So photons carry radiation, or are radiation that carry energy as light or heat or X-rays or gamma rays. Okay, and the way we define radiation for like accident purposes and medical purposes is by what effect it can have on living tissue. So ionizing radiation is any radiation that can cause electrons to be stripped from a molecule. So when you strip an electron from a molecule, whether it's part of a desk or part of one of your cells, you're changing its ionic charge, and that's why it becomes ionized. If you add an electron, it becomes a negatively charged ion. If you strip an electron, it becomes a positively charged ion. Ionization is important because a lot of chemical reactions happen as a result of or include ionization. When you take hydrogen and oxygen and put them together, they share electrons, and so one of them has to be ionized before it can form an electron bond and become a molecule. You get H2O, so you have two hydrogens and oxygen. That's water. If you ionize it strongly enough, or if you ionize it, you take away with electrons, that can destabilize the molecule and cause a chemical reaction. You could strip the water into separate hydrogen. You could change something that's in a protein to break a bond. And in biological systems, proteins are everything. Proteins are what our bodies are made of. They're what we use for signals and enzymes, and are what we use for signaling between cells. So changing them can change the nature of the cell. We also change them, which is temperature. Simple bonds, or ones that are not very strong, can be changed by heating something up. So when you put an egg in a frying pan, the proteins in there change from a clear kind of viscous liquid to a more solid form just because we're doing a chemical reaction. But atomic reactions and ionizing radiation can cause really strong bonds to change. So when you cook something, you don't actually break down the DNA in it. But an ionizing event can actually break the bonds between the atoms that make up the DNA molecule and change the programming of the cell. So all these things happen when we get exposed to radiation. Sometimes the radiation will hit a water molecule and strip it off. We get a free oxygen or a free hydrogen or all of them. But if you have free oxygen in your body, it's a useful chemical. It's a useful chemical, and it just recombines very quickly. So ionizing the water in our bodies doesn't cause much of an effect, which is why we can absorb, lots of radiation every day from sunlight, UV, and even from medical procedures or the accident in Fukushima without any noticeable effect. Because most of the ionization events that happen to us aren't anything that causes significant medical alteration. But a few of those changes are going to actually be the radiation is going to encounter the programming of our cells, which is our DNA. And if it breaks the DNA, breaks a bond, again, the most common reaction is that the cell will reconnect it and it becomes back to its program. If it breaks it on certain places or at certain times, it's kind of random, the DNA becomes permanently broken, and now the program for that cell is damaged. Again, most of the time, the cell dies. Okay, your body may recognize it as different, or the program for that cell is no longer viable, so now it's a dead cell, and your body cleans it up as waste material, the same as from any other ingredient. But on rare occasions, it's possible to change the programming such that the cell isn't killed, but it becomes something that's close enough to us to be not recognized as foreign, but still viable enough to live and grow, sometimes prolifically, and that's what we call a cancer. That's where tumors come from. These are misprogrammed cells that proliferate and take over resources.
So first, maybe that's a good point to stop. Any questions, first of all, on what he said so far? Nothing?
Okay, so backing up to the what types of radiation, the things that can enter our body and break these bonds are basically anything that you can actually break the bonds in DNA mechanically. Okay, it's theorized that lung cancer caused by asbestos in people who had asbestosis, that the fibers of the asbestos are so sharp that they can actually poke into the cell and catch on the DNA strands and break them mechanically. But most of the time it's done by chemicals or enzymes or high energy events. In the case of ionizing radiation, it's always the absorption of energy from a photon or a subatomic particle that breaks the bonds. Okay, the heaviest radiation carriers are alpha particles. Alpha particles are stripped helium nucleus in that there are 2 neutrons and 2 protons, and they happen when a large molecule like uranium splits and there's an extra piece left over. That piece is thrown out with some high energy, and it carries mass and can just bang into things. Because it also has protons and it's positively charged, it can break electron bonds. However, because alphas are so massive, they tend to not be able to fit through the holes in matter. So they get stopped by even light matter like a piece of paper. The energy is absorbed on the surface because they have a large cross section, so the fact that the atoms of the paper are loosely spaced, the cross section of the alpha is so large that it probably will encounter one of them, and so it doesn't get very far. Sometimes it'll bounce off of one and lose energy, but even just going through some generally empty space like air, an alpha particle has a mean path length of about 30 centimeters. Okay, high energy alphas go a little bit farther, but they lose energy along the way, banging off of air molecules, and sometimes they bounce around. The second most common kind of radiation, and actually the kind we're dealing with the most in Japan, is beta radiation. Beta radiation is one of the electrons that was left over when the atom split or when the decay happened, or a positron. Positrons are anti-electrons, and actually what cesium gives off, but for most purposes we can just say it's an electron. They have a negative charge, they have a small cross-section, a low mass, and hopefully generally low energy. Depending on how they were emitted from the atom, they may have a higher or lower energy. And in fact, we can tell what they came from by what their energy is. But again, it's difficult to measure the energy of them because they lose energy as they travel through space, either by hitting other molecules or because they have an electromagnetic charge, they can be decelerated, accelerated, or curved by a magnetic field. And we'll demonstrate that a little bit later with a strong magnet. The most penetrating radiation is X-rays and gamma rays. Okay, X-rays and gamma rays are a little bit fuzzy as to where they change from one to the other. In the electromagnetic spectrum, we're always talking about the movement of photons. Photons are the fundamental particle of electromagnetic waves, which includes radio, light, and X-rays and gamma rays. Gamma rays and X-rays are the very shortest of the frequencies, and in electromagnetic spectrum, the shorter the wavelength, the higher the energy. So we can say that the color of red, and a little bit outside of what we can see infrared, we call those heat waves because they have so little energy they can't do a lot to bonds, but they can agitate molecules and increase their temperature. As you get shorter and shorter in the wavelength, the color gets changes for our perception until we get through oranges and yellows, greens, blues, and eventually violets and ultraviolet. Ultraviolet is on the short end of the visible spectrum, or just outside of it, and has enough energy that sometimes we consider ionizing. Ultraviolet radiation can ionize molecules, but only not very strongly and often not at all, because depending on how the bonds of the actual molecule that it reacts with, the atom that it reacts with, it may not be able to ionize it. Above that, we start talking about X-rays. X-rays and gamma rays always have enough energy to ionize the chemicals that make up living organisms. So they're very likely to cause an ionization if they're absorbed. But they have so much energy, or they're so short a wavelength, that they aren't strongly reacting or interacting with our matter. So most of them pass through things. Consequently, when you're in a gamma field, most of the radiation goes through you, and the few that are absorbed cause ionization events pretty much anywhere in your body. They are absorbed more based on your density. In fact, this is how we make X-ray images. We put film behind you, we put an X-ray source on this side, and we shine it through you. And the fact that there are, let me stand in front of that. And basically, we're looking at the shadow. So the film turns dark from the gamma rays, also, or from the X-rays. And so where more of them come through us, the film turns dark. Where it doesn't come through us as much, it's light. This is how we make an X-ray image, because our bones and the more denser tissues of our bodies absorb more of the X-rays than the rest of it, and we basically make a shadow graph. Okay, you can do the same thing with a bright light. If you shine a bright light through your hand, you can kind of see the bones, because the soft tissues and stuff, light comes through, looks kind of red, but the bones are dense. So the same thing works at a visible spectrum, but it's not enough to be able to shine them through our chest or something. I imagine if you had a bright enough light, you might be able to see something. But X-rays pass right through us. We only absorb a few of them, and we're able to see the difference in a film image.
Gamma. Can I get back to the short ultraviolet?
Short ultraviolet.
Is that what induces cancer when people get too much sun exposure or from tanning beds?
The ultraviolet rays, the longer ultraviolet rays are enough to trigger our cells and force the production of melanin, which gives us a tan. The shorter waves break bonds and actually cause a burn, and that's where sunburn comes from. Sunburn is a radiation burn. It's the most common radiation burn that is encountered by people, and is the source of, it's also why skin cancer is the most common cancer in people, especially ones that have outdoor lifestyles.
In other words, is it an ionizing event in the DNA from the ultraviolet?
The ultraviolet that causes tanning does not affect the DNA. The trigger in the cells that generates melanin is a chemical reaction. I can't remember, but it's not at the DNA level. It's not nuclear, not cellular nuclear. It's not in the nucleus of the cell. It's in the outer parts of the cell.
It's more of a chemical reaction.
Yes,
based on melanoma production.
Well, all ionizing events, even the gamma rays that change our DNA, that's a chemical change. The ionization event causes a change in the DNA molecule, which is a chemical reaction induced by the radiation. The reason we make a difference between, like now we're saying UVA, UVB, and UVC is because the shorter waves, for people who want to get a suntan but don't want to get a burn or get cancer, they try to put something on their skin that'll block the shortest waves in order to get the ones that are least harmful and trigger the melatonin response and get darker skin without hopefully
melanin.
Sorry, melanin. Melanin. You're right, melanin.
Melatonin is what you take for sleep. You know about it. Right. Okay.
No,
is he going too fast? We're good? You're following? Yeah. Okay, you can slow down a little bit.
Well, feel free to interrupt me.
Yeah.
But yes, where the transitions from, the transition from UVA, UVB, and what they do to cells are kind of like colors. Where does orange become red? Where does yellow become orange? Is a little bit subjective. The same thing with the UV rays. Clearly, the stuff that's the closest to visible, 450 or so nanometers, is not going to cause a burn unless you get really intense. The shorter wavelengths, 380 or so, where it's deep UV, that's going to cause a burn before you not help you get tan at all. Which actually leads us to one of the units.
And you can write on the board.
Yeah. That's a good idea. You're familiar with scientific prefixes? I just used several of them without really explaining them.
Right.
Okay. So when I talked about UV radiation at 480 nanometers, that's the distance. If you measure the photons that go on, they have a characteristic wavelength. And the distance between those waves, we express in nanometers, hundreds of nanometers. Okay. Visible spectrum is in the 530 nanometers is green, 700 is deep red. Longer than that, at 1,000 nanometers, which actually becomes 1 micron distance, that's what we call infrared. Okay, in infrared, we can sense indirectly. We can feel it on our face, we can feel it on the back of our hands. If there's enough of it, you can feel it even with the palm of your hand. But that's how you tell you stand there heated, you can feel it's warm. That's actually the infrared light shining on you. You can't see it because it's outside the visible spectrum, but you can definitely sense it. Okay? We use these same prefixes for all of the scientific units that we talk about. When we talk about the measurement of radiation, whether it's becquerels, which is a unit for measuring the quantity of a radioactive substance, either on a surface, in a material, or something. We talk about microbecquerels, megabecquerels, although the becquerel unit is so small that we almost always talk in kilo, mega, or petabecquerels. Okay, this is 1 times 10 to the minus 369. Okay, and then we have the unit, which would be the way we're doing it. It's kilometers for say meters for distance. Weight. Well, weight, we're not going to use weight because that one's confusing. And we're not going to use seconds because nobody talks about megaseconds or milliseconds. When we talk about milliseconds, we don't talk about megaseconds. I often confuse people. I say, well, that was 150 megaseconds. And it's useful for calculations, but most people, when they go above seconds, they just transfer it into weird units like hours or days or years.
How many days is a megasecond?
Huh?
How many days is a megasecond?
Well, the one I actually use is weeks because it's easier. A milliweek is 10 minutes. Okay. So a milliweek is 10 minutes because there's about 10,000 seconds. It's very close. So you can kind of calculate for those. It really works out when you're doing relationships. You usually convert the units back for multiplication, but we're actually calculating. I have been known to work in megaseconds and which is hours. So going the other way, going positive. Kilo is 1 times 10 to the 3. 10 to the 6 is mega. 9 is giga. And 1 times 15 is
Yeah.
Terabytes.
Right. Yes. We can think of it in terms of bytes.
Yes.
How big is my disk?
Bytes. But bytes are a different case. We don't use these units. We say
Terabytes.
terabytes and gigabytes. But we're
Megabytes?
actually use gigabyte is actually like this, and it's actually 2 times 10 to the. I have to start at the bottom.
Maybe Frank
kilo
knows.
was 2 times 10 to the 10, 2 times 10 to the 20, 2 times 10 to the 30.
Yeah.
And it's actually slightly different because a kilobyte is 1024 and a megabyte is 1.2 billion.
But anyway, that's the same prefixes and same.
Same prefixes, we pronounce them the same way, but specifically in binary, we use binary units for those, but that's a separate whole subject. Okay. So the amount of radiation released from Fukushima in terms of the total release into the ocean is generally listed in petabecquerels. So
Well, you didn't explain becquerels.
becquerels.
Becquerels, sieverts, grays.
Right. So the units for radioactive materials, or we want to talk about when we're talking about radiation, are. Let's go up. And there are a couple. These are we could say that it's metric versus imperials, like inches versus meters, but they're really all they're all decimal systems. So even the Curies and Roentgen and stuff were decimal, and so we're nominally metric. But they weren't SI, which is the International Scientific Standard. So, in fact, I used the ones on the right most of my life until the disaster in 2011, and just because that's what's standard or customary in the United States or was customary in the past. But becquerels, which basically replaced Curies, but are a much smaller unit. In fact, I don't even remember the definitions for the Curie. It was the Curie was based on a particular sample that was a certain amount, and it was basically random. kind of like, I guess, the foot would be the length of the king's toe to his heel. But the units that we're using as standard now are becquerel, sieverts, and gray. Becquerels are the measure of radioactivity, in that any substance that's radioactive is going to have spontaneous decays in it. And if it's decaying at 1 decay per second, that's 1 becquerel. So by mass, so the amount of material you have, the amount of becquerels it puts out is a function of how much you have in mass, or quantity, times its radioactivity. And radioactivity is inverse to half-life. So things that are very active, have a very short half-life, like iodine and some of the even more volatile isotopes, they decay very quickly. The half-life of iodine-131 is about 8 days. So it doesn't take very much of it to get a lot of radiation off of it. Okay, things that are not very, or that are very relatively stable, like say plutonium, has a half-life of 22,000 years. So even if you have a gram of it, you don't get a lot of radiation off of it because not very many of the atoms are decaying very often. Okay, it's the things kind of in the middle, things that have half-lives of a few years, like cesium-134 with a half-life of 2 years, strontium-90 with a half-life of 28 years, that are the most harm to people because they're radioactive enough that they give off a lot of radiation without a large quantity. Iodine, hugely radioactive, but it's gone in just a few days. You know, if the releases that were made, that came out of the nuclear disaster in Fukushima, we didn't even get a chance to measure the iodine carefully because by the time we and even most scientists could gear up, it had decayed away to levels where the uncertainty outweighed the measurements we could make. Because the rule of thumb we use for radioactive decay is 10 half-lives, and it's gone. So in 80 days, the iodine-131 was below 0.1% of the original quantity, and it's hard to find it. The same thing goes for the cesium-137, which is the most prominent contaminant in Japan, has a half-life of 30 years. So we say it'll be around for 300 years. Obviously, at 300 years, you'll still be able to find a little bit of it because it's a reverse exponential curve. But at that time, it'll be less than 0.1% of the original quantity. Right now, the cesium-134, which was at the time of the accident equal to the cesium-137 by activity, so there was the same number of becquerels of cesium-134 and cesium-137 right after the accident. This is what fell on Tokyo, what fell on most of Fukushima. That means that there was about 15 times as much cesium-137 by mass as there was cesium-134, because in order for them to be equal by activity, they must have an inverse relationship between their half-life and their mass. Right now, we're 4 years out, so how much of the cesium-134 is left? Has a half-life of 2 years. Well, after 2 years, it was half of it. After 2 more years, it's half of that. A quarter. 25% of the cesium-134 still remains. In fact, this is how we know contamination found on the west coast of the United States or the places in the world is from Fukushima. If you look at the ratio of the cesium-137 to the cesium-134, because Chernobyl is another big source of the contamination. Okay, and Chernobyl put out also not quite as equal as Fukushima, but the effluent from Chernobyl was also comparable. They were within a factor of 2 at the time of the accident. So now with 25, 30, well, it's been 32 years since Chernobyl.
Not 32. It was 86.
86.
Not quite 30 years.
Oh, sorry, 29 years. It's 29 years. So at that rate, the 134 is essentially gone. So you only find the 137. When we find contaminants on also in the world, and we find the ratio of 137 to 134 is, well, this year at a ratio of about 3 to 1, 4 to 1, then that's probably contamination. Or actually, it's a signature for it. It was recently emitted. Okay. Questions about becquerel?
Questions. Let's go for this. So why don't you write becquerel on the...
I would, but I can't spell becquerel.
B-E-C-Q.
This is one of the ones I always rely on.
E-R-E. And it was named for Henri Becquerel.
Yeah. All of these names all come from prominent researchers in radioactivity or atomic phenomena.
So what's the most useful, what do we use becquerels for the most when we're measuring radiation?
The most common usage of becquerels, we're talking about a quantity of radiation. So when we talk about the standards for cleanup in the exclusion zone, the standards for foods that are allowed to be sold in the market, those are always expressed in a ratio of becquerels to whatever the numerator is. So for fluids like milk and drinking water, that's just expressed in becquerels per liter. In dry foods like rice and vegetables and things, becquerels per kilogram. Okay, for contamination in the outdoors, we usually express it in becquerels per square meter. So how many disintegration events are happening in that area over time? And the standard that the standard that the Japanese government has set for repopulating the evacuated areas is I can't remember what it was in becquerels because they usually express it in sieverts. It winds up being about 20,000 becquerels per square meter. But anyway, they're actually doing sieverts. I moved ahead wrong because it says we actually use sieverts for the standard. So before we move on from becquerels, do you have any other questions?
I have a question about the range of beta rays. You were talking about like the range of alpha rays is around 30 centimeters.
Is that
The range of
range of beta rays?
You said alphas or
Alphas have a range of 30 centimeters. Betas generally have a range of a meter or so in air, but it depends on how much density is there. Okay, an alpha has a range of less than a micron in wood. Okay, so we won't get through paper because paper is wood pulp. Betas, so those are electrons, those have a range of anywhere from a meter to 10 meters, sometimes 15 meters in atmospheric air if they're very energetic. In a vacuum, of course, they go to infinity. But in a general environment like this, the energies that are coming off of cesium, the beta has a range of about 1 to 2 meters for 90% of them. Okay, for the absolute limit is about 10 meters, but the number of them that get that far is very, very small. So generally, if you have a beta source and you put a Geiger counter near it, more than a meter away, you get a significant, you don't have anything significant to pick up. Gamma rays, they are very penetrating. They'll go through 50 to 100 meters of air for 50% of them, or centimeter of lead, 4 inches of earth, 10 centimeters of concrete, or about 30 centimeters of water. Depends on there's a few variables depending on how energetic it is and what the actual density and cross section of the shielding material is.
So in terms of the nuclides from Fukushima, for instance, cesium-137, cesium-134, iodine-131, strontium-90, what kind of emissions, what kind of particles or rays are they getting?
Well, that's one of the things that wasn't covered in the video, is that when a radioactive nucleus or a radioactive isotope decays, it has a couple of possible ways to do that. The unstable nucleus kind of shakes around and tries to rearrange itself, and there's usually a prominent method. I mean, if it has too many neutrons, it tends to throw off if it has too many neutrons and protons, it tends to throw off an alpha, and through alpha decay, it stabilizes. And when you...
An alpha is 2 protons and a neutron?
2 protons and 2 neutrons.
2 protons, 2 neutrons.
Yes, that's true.
That's an alpha.
That's an alpha.
Much right there. And the beta is?
Beta and I usually say beta particles, but some people say beta rays.
2 protons,
2 neutrons, yes, is one piece. Now, two neutrons and 2 protons is the same as helium. But normal helium has 2 electrons orbiting around it. The most common fate of an alpha particle is to bang into something, knock a few electrons off of it, gather those electrons, and turn it into helium. Okay, this is why there's helium in the world. Okay, the Balfour particles that are being generated deep in the Earth become helium. They rise up through the geology. They get trapped underneath rock domes and things. So when we drill for natural gas, we often find helium mixed with it. Okay, if the helium gets to the surface, it's so light it floats away like a helium balloon and blows off into space. So all the helium we have that we can use for balloons or talking funny or other more scientific purposes is as a result of natural or induced, because we can make helium in reactors we want to, radioactive decay deep in the Earth.
So what is a beta?
A beta is basically an electron. So 1e. Okay, but actually there are two kinds of betas. There's both positive and negative. So it could be an E minus or an E plus. An E plus is actually an anti-electron and is we say a positron. Sometimes those are generated. They usually, actually the radiation coming from our cesium is indirectly positrons. But it has the same effect on the molecules it encounters as electron. It disrupts the charge, ionizes the molecule, can cause a chemical change or be absorbed. It can also encounter an electron if it gets close enough and annihilate.
And a gamma?
Gamma is a photon.
So why is it called a ray?
Photons are mysterious little critters that are one of the fundamental parts of the universe that we don't necessarily understand perfectly, because photons can be described as a particle, and they have properties of particles in that they bounce, they react, they interact with things, they carry momentum. Okay, but they also interact like waves. Okay, and so some of the fundamental theories of existence say that everything we have, every instance of matter, is just a vibration or a disturbance in the strings or the fundamental makeup of the universe. So in those ways, each of those things is kind of like an echo or a sound wave. And photons are the ways those transmit, move between, through places in time. I can't explain it perfectly because I don't understand it perfectly. I know how to manipulate photons. I know how to detect them and measure them and know their characteristics, but they're fundamentally mysterious in a lot of ways.
So what's coming out of cesium-137?
Talking about cesium-137, we actually come to an interesting wrinkle in that, and actually let's back up and do strontium first. Okay. Because strontium-90 is another one of the common fission fragments that's in a uranium reactor. The way we make electricity from uranium is we put uranium into a reactor vessel, we bring enough of it close together that the neutrons that are coming out of it, because uranium naturally decays sometimes where it gives off a neutron. The neutron gets absorbed or bangs into a water molecule and becomes deuterium or something. But if it hits another uranium nucleus, there's a chance that nucleus could split, giving off more neutrons. U-238 will absorb neutrons and split and give off neutrons, but the number of neutrons it gives off is about the same as the number of neutrons it absorbs. So there's no sustainable reaction. It's very difficult to get uranium-235 to cause a chain reaction. Or sorry, U-238. But U-235 is more unstable, so when it splits, it tends to give off between 2 or 3 neutrons. So there's a gain there. So you put in 1 neutron, you break the nucleus, and you get off 3 neutrons, and those hit nearby nucleuses, and we're doing more, and the reaction builds up. The trick to controlling a nuclear reaction in a reactor is managing that cycle. So if you put things in between the spaces that absorb neutrons, you sort of break the cycle, and there's more of them absorbed that are generated, and the cycle breaks down, and the reaction stops, of course. And if you pull those absorbers out, and there's enough uranium, enough fissile material close enough together, then the reaction self-sustains. And it's a little more complicated than that because the neutrons given off by splitting uranium aren't actually likely to cause another split. They're too fast. They tend to bounce right through and bang off, and they don't get absorbed and cause a splitting. We need to slow them down first to make an effective reaction. And that's what's requires something we call a moderator. The moderator slows down the neutrons to the point that it increases the likelihood that they'll be captured and cause a splitting in the fuel. And in most of the reactors that we use for power generation, we use a water moderator. So the water that's surrounding the fuel rods has a number of purposes. It cools the reactor, it brings the energy actually out because we can circulate it through to make steam and turn the turbines, but it also is a part of the nuclear reaction in that it slows down the neutron in order to enhance the likelihood of a reaction.
So where does the strontium come from?
The strontium comes, and all of the other things come from. When we do break the uranium nucleus, this big chunk of protons and neutrons splits. And, well, like from the video, the number of protons in a nucleus determines the element. That's how we define an element. Something with one proton is helium, something with two, or with one proton is hydrogen, with two it's helium. Okay, so uranium tends to split on about 1/3 and 2/3. So the fragments that are left over tend to have about 1/3 to 2/3, or between about 130 and 150 particles, 30 or 40 protons to each number of neutrons, or between about 45 protons and 40 neutrons. So one side of it becomes things like strontium-90 with, I forget the number for strontium, but it's 90 total, so it's probably about 48 or so. I'm
not sure, but we can
find out. We have a chart for
It's
number.
atomic number, right?
Huh?
Yeah. Atomic number.
Is 38? Yeah.
Good.
So it has a lot of, obviously then if it's strontium-90 and it has only 38 protons, it has a lot of extra neutrons, which is probably why it's radioactive.
Mm-hmm. And so what does it give off?
Strontium decays, I don't have memorized the decay chain for what strontium goes into, but it gives off a beta. It gives off an electron.
Mm-hmm. That's why it's not good in your body.
Well, strontium, it's radioactive is why it's not good in your body. Strontium is a special concern and was a very scary isotope after Chernobyl and after Fukushima because, one, it's a pure beta emitter. And because it's a pure beta emitter, it doesn't give off a gamma, and its daughters don't give off gammas. It's very difficult to detect with the gamma detector. Okay, the way we, this is, we're jumping ahead of cesium-137 is also a pure beta emitter. So we could not detect it with a gamma sensor either, except that the daughter, in other words, when cesium-137 decays, it makes barium-137. And barium-137 is actually very unstable, has only a few minutes half-life, and is a gamma emitter. So the gamma rays we see when we measure cesium-137 are actually coming from barium. But we label it by convention as being from cesium because we know that barium couldn't be there by itself. With only a few minutes half-life, it would all be gone before we could get their instruments out, except for the fact that it's constantly being generated by the decay of the cesium, which is the isotope with a half-life in human terms. It has a half-life of 30 years or about a generation. So we talk about it being the isotope that we're detecting. We did the same thing when we talk about the health hazards of radon. Okay, radon gas is a daughter of uranium with a half-life in days. So the uranium or thorium decays in the deep ground, creates radon gas, which then, because it's a free gas, can percolate through the soil, winds up in your home. If you inhale it and it happens to be unstable at that time and decay, it becomes polonium. Radon decays to polonium. Polonium is a metal, and the emission, even though it's not gamma, because it's a gas, it's in your lungs, it can directly affect the tissue if it's very close by, and that's why we think radon is. That's why radon is a hazard. But we talk about the radiation we detect from that in terms of the radon, not the polonium, because the polonium is a lot.
So then cesium-134 is just my screensaver.
Is it?
Yeah, just hit the mouse, hit the track.
I can like it.
Okay, fine. So cesium-134 is also a beta emitter?
Cesium-134 is a gamma emitter. Actually, the route that an isotope can take, sometimes it'll throw out a beta, and sometimes it'll restabilize by throwing it to gamma. So for the case of cesium-134, it has about a 75% likelihood of throwing out a gamma and 25% throwing out a beta, or maybe it's vice versa. Mm-hmm. Anyway, it's about three-fourths to the other. And those different energies are how we identify cesium-134. We look at the energy on a spectrum, and say, oh, it's got the characteristic energy, these two peaks in this ratio, it must be cesium.
And then what about iodine-131?
Iodine-131, I'm not as familiar with its other decay modes, but the primary decay mode is a gamma emitter. I don't remember the energy, but it's a gamma emitter, yeah. But some isotopes, one of the most common isotopes, radioactive isotopes that came out of the reactors is xenon. Is an isotope of xenon, I think xenon-155. But xenon is chemically an inert gas. So it doesn't react in the environment, it doesn't react with our bodies. There was probably a wave of xenon that came across Tokyo in the early days of the disaster, which caused an exposure to people, but it blew away, and as soon as the wind blew by, the xenon was gone. The other isotopes like iodine, strontium, and cesium are more problematic because, and this is what we were talking about before, about the difference between the substance and its smell in chemical terms. Because the cesium might irradiate as it goes by and it decays, we get the gamma radiation, but it also reacts with things chemically. Okay, strontium is similar in its chemical properties to calcium. So if in our bodies, if we inhale some strontium or it's something we inject, we eat, or something we drink, our bodies treats it like calcium, and it replaces the calcium in our bones or our teeth with strontium-90, and it stays irradiating us for many years. The half-life of strontium-90 is about 29 years, but the biological half-life, in other words, if you get strontium in your body, how long does it take to move out, is longer than that, 60 or 70 years. Okay, so the physical decay dominates the sort of the biological equation. Cesium-137, on the other hand, the body treats chemically, or in biological systems, is a lot like potassium. So potassium we use in our metabolism, in our muscles, and so our body has to use it, exchange it. It's in our excrement. We exhale it, and so it's sort of flowing through our body. So if we bring in cesium into our body, it basically gets exchanged for a new chemical, either new cesium or usually more potassium, in about 100 days. So even though it has a physical radiological half-life of 30 years, we would have only an exposure to it in our body of about 3 months.
Okay, so maybe we'll take a few questions, and then if you have some demonstration about measurement,
yeah.
And then
well, actually, there should be a lot of questions for that. I didn't cover that.
So questions, gentlemen.
How can the radiation spread so far, even though like the range of tests is pretty short?
Because the difference between the material. Okay, when you look at the people who go into the nuclear power plant or went into the zone early on, we're wearing Tyvek suits and gas masks and all these coverage. Those suits don't protect us from radiation. The gamma rays go right through, and we're still being irradiated while we're there. But there's also the material. The cesium is stuck to things. It's in the dust. It's in it's on the plants. It's everywhere, and that can get stuck to us, or we could inhale it. So we use that protection so that when we leave that area, we leave that stuff behind. Even if some gets on us, if I fall on the ground and get the dirt on me, there's cesium on my arm, I can take off the suit and leave the dust behind. This is what I was talking about, like why it's like paint and the smell of paint. When your room has just been painted, you can smell the paint. But if you leave the room, you no longer smell it because you've left that space. But if you lean against the wall and get some of the paint on you while it's wet, and then you go to another room, then everybody around you is going to smell that paint because it's still emitting the volatile chemical. And the radioactive material is similar. If you get it on you or in you, you take it with you, and you're still being irradiated. So, in fact, the cesium that came from the plant moves easily through the systems of our atmosphere. Okay, cesium is a highly reactive chemical. As soon as it encountered the steam once you get out of the metal rods, it encountered steam or liquid water. It strips the water and forms cesium hydroxide, which is itself still reactive, but is soluble in water itself. It's hygroscopic, so it can mix with the humidity in the air. So the cesium came with the air the same way that moisture comes with the air. When the temperature changes or the pressure changes, it can condense the same way that clouds and raindrops and snowflakes are formed. And then it fell, touches the ground or touches the buildings, and depending on what they're made of, it may be get another chemical reaction. Okay, if it's clay or stone or even cellulose, like from wood, then it forms another reaction and forms a compound of cesium. That compound, since since it includes a radioactive form of the cesium, is itself become radioactive. In fact, I have a piece.
Yeah, so maybe on this table is a good place, I think.
Yeah. This is a piece of wood that was part of a deck in Koriyama at the time of the disaster. And this is a Geiger counter. Okay. Now what a Geiger counter does, a Geiger counter is a kind of vacuum tube. There's a low pressure gas inside, and a couple of electrodes and some conditioning to make it effective in certain ways we cover. But basically what we do is we charge it up, and it charges up like a capacitor. And you get a lot of tension between the two electrodes in the tube across the gas. But the gas is kind of stable enough that it has all these extra electrons, and it just sort of, it maintains itself. Okay, just barely. We put enough voltage on it that it's sort of on the edge. But an event happens that knocks electrons off, an ionization event, knocks some of the extra electrons off the gas inside, and that electron knocks the electron off the next one, and it causes what we call an avalanche. So all of those extra electrons we've stacked in the gas start moving around. They move to the electrodes and conduct through the wire and make a pulse. Okay, so any type of radiation that is ionizing, that is able to strip one of those electrons and start that reaction, will discharge the tube and cause a click. Okay, and then the circuit in there charges it back up again, and the same thing can happen again. This happens very quickly, so it can actually happen tens of thousands of times a second if necessary. And the clicks you're hearing from this are because of random events that are happening all the time. Most of them will be events from outer space. A lot of particles come from distant stars or from our sun that are very energetic, and they hit gas molecules in the upper atmosphere, generating all kinds of other secondary effects that we call cosmic rays that are most of the background here. Some of this background will also be from the building materials around us. The walls are made of gypsum, which was mined from the ground, which probably includes a little bit of thorium. In Japan, not a lot, so it's locally made gypsum. It probably isn't, it's not very radioactive. Everything has some radioactive substances in it. Even our bodies contain carbon. Carbon-14 is slightly unstable, so it has very long half-life, so it's not a lot of it. Potassium, a certain percentage of potassium is potassium-40, which is radioactive. So that's where these backgrounds come from.
So is my drawing good? So this is the Geiger GM2, Geiger-Muller 2.
Geiger-Muller for the guys who know.
And this is the thing that's different kinds, and inside is this gas like argon.
It's usually helium.
Helium,
Mostly
argon,
helium and neon.
and there's a positive charge, a negative charge,
Yeah, positive is the anode,
right?
negative is the cathode.
But they don't connect usually because this
Right.
gas doesn't conduct electricity. And then something comes through like a gamma or a beta,
Yeah, anything that'll knock an electron off from the gas
and
molecule.
it hits one of these little gas things, and that puts off a lot more electrons.
Well, it causes a chain reaction of electrons.
And that makes an electrical
cascade.
connection through the gas. Makes the gas conduct electricity, and then that sends a little electric pulse. And then that little pulse is what is converted to a sound or a loopy light. So that's how a Geiger counter works.
So this piece of wood was part of a deck in Koriyama, and when the fallout came down, it came down with the moisture, maybe as rain, probably as either a light mist or maybe as dew. We don't know, but we know it didn't saturate the entire piece of wood, didn't run around the bottom, because the bottom of it doesn't have any crystal activity. We put it against the Geiger tube, the background counts up a little bit, but not a lot. But the top is very active. Okay, the top is coated with cesium-137 and cesium-134, and is still emitting even almost 5 years later. And will be for as long as this piece of wood is around. Okay, in 30 years there'll be half as much of it, but it'll still be detectable certainly for all of our lifetimes.
What else you got?
Question? We're still doing. Did I cover your question about how does it move so far if it only has a short range? But then also, if you look, you see the betas coming off the reactor are quite short range, and partly that's because this has been varnished after the cesium on top of it. So the electrons that have to get through, they have to get through the layer of varnish, and that decreases their range quite a bit, because by the time they get to the varnish, they've lost, the ones that do get through have lost half their energy, and they don't go as far in the air. And so I did not. The person who owned the deck, they were building the deck at the time of the earthquake, And so the wood was actually there the weekend before. They put it down the weekend before the earthquake. The earthquake was on Friday.
Yeah.
And a week later, they then varnished it because they'd already made plans for that. So.
Yep.
No,
So they sealed it in.
Yeah,
So
they
that
sealed
makes
it in.
nice-
Makes it good because you
a
can
nice-
touch it and you actually can't.
Yeah. Not gonna get it.
It also means that even a short distance away, it's fairly safe to handle. Some things give off a lot more beta radiation. And this is a strontium-90 sample. Strontium-90 is a pure beta emitter, but the energy that strontium-90 gives off and the energy that this detector is sensitive to are a good match. So it has a huge sensitivity to it. So it has a very active reaction.
You mean the strontium was a beta?
Strontium's a beta, right?
6,600.
Oh, more. That's just, it has a...
That's
a
the
minute.
first.
Yeah, it has a 1 minute time constant here. So it'll take a minute for it to stabilize. It'll be in the hundreds of thousands. Yeah, it's already at 165,000. 167,000. Or 200,000 count per minute.
And show how fast the drop off is.
Oh, it is. So
How
most of
far
them
do you
are
have
only
to
going 2
get-
centimeters. Yeah.
How far do you have to get it so that it is not so different from ambient?
Probably about a meter. Yeah. I think if we let this count, put a shield between it and the sensor, like, I don't know, a bunch of meat, and let this count for 20 minutes, it would probably build up. Then you put it here, a meter away, you'd probably see about double. It doesn't sound very different, but it would accumulate.
Did you bring anything that would be a good shield?
Me?
You? Okay. How about my hand? How about my hand? Look at that. It basically
No,
works.
we don't even need that much. But you can put a piece of paper.
Okay, here's a piece of paper.
So betas go through paper. But your whole book, put your notebook. Most of it.
Yeah.
Okay. One of the interesting things about betas, though, is that they are charged, which means you can steer them with a magnet.
Check up.
Okay.
Oh, hold the checker.
We put this here, so it's kind of going in every direction. And depending on which way I face the magnet, I can either add or cancel. Right. More space. And I have to try to this magnet before. And that can shield it. That's just putting metal between them. Like that. I want to just have enough room that it can just be there, then I can move up and down.
How about I put this horizontal?
What we want to do is get 90 degrees so we can turn it. And maybe that this is a dual pole magnet, it just makes the electron go like that and makes an S shape and actually go the same way.
This work here.
It did. What was it magnet? The one you really want to have is where you increase it so that where you're adding turning the ones that come forward. It's not working well. I need to get a magnet that I can't get into this and have a little frame on it. Oh well, like this. Okay, this way, the thing it's shielded. We might be able to make them bend around. This doesn't matter if this. That way you go through, some one around this way. And that way it's pretty much silent. It's probably bending them away from the detector. This way, it brings it toward. And you get another frame. And find the right orientation. Because one that I did this for a couple years with Michael Goldberg. I had like 50%. I was able to change it from 200 to 400, or from the 200 down to 50.
I've seen this with at that summer.
Yeah, summer camp.
Yes. So is there what is unusual or special about how Safecast measure radiation?
Well, one of the things that Safecast does, one of the things that we don't, or that is characteristic of our way we make our measurements, is we use Geiger tubes. Okay, so the Geiger tube doesn't know what kind of radiation triggered it. It's like sitting in a car and somebody throwing change at the car. You hear the coins hitting the roof, and you can maybe count them if you listen to the sound, but you don't know how much money they're throwing. It could be nickels, it could be dimes, it could be 100 yens, could be 500 yens, but we count them all the same. We just count the pulses. So the actual dose rate that we convert from this, look, this is displaying in count per minute, CPM. That's just the number of events. In order to convert that to a dose rate, you need to know what the source is. And in fact, using this strontium source at read 16,000, it would not give an accurate dose read because this has been calibrated for season monthly cell. So the dose mode, we know what the contamination is in Japan now. It's cesium. So we use a conversion factor to get to dose rate based on what we know about the tube and what we know about the contamination. And we do that by having a few detectors that can tell the difference. We have a simulation detector for large. It's a very expensive, very sophisticated piece of equipment that costs a lot, but we use that sort of to leverage to a lot of very inexpensive detectors. So using that, we were able to characterize what the contamination environment was and know what factors to multiply the number of counts into a dose rate. But in other places, if you take it to someplace outside Japan, except for Chernobyl, where the contamination is about the same, the conversion factor could be substantially different. Okay? So we use 2-inch pancake tubes, which are have a high sensitivity. So with low dose rates, we can still get enough counts to get statistical significance in a short amount of time. And it has a good efficiency for picking up a reasonable efficiency for picking up the emissions of the contamination that's present in the
Mm-hmm. I don't think we talked about sieverts really in grays.
Sieverts and grays. Another unit of measuring radiation is a gray. A gray is an amount of exposure. So its amount of unabsorbed, how much radiation is absorbed. Okay, so, and again, that's, if one substance is emitting a certain amount of radiation, if most of it goes through, then the amount that's absorbed in something, like the amount absorbed in the wood for the radiation goes that way, we would measure in grays. Okay, and that's a function of how dense in the cross-section of the energy of the material.
So for instance, if I had, let's say I had a popcorn popper, and it was spitting out hot popcorn, then the rate that it's spitting out the popcorn is the becquerels.
It's the becquerels, right.
Now, this popcorn, I'm shooting at you, and they're hitting your body.
Well, actually, what I usually do is I say I have a bucket next to it, and how many are falling on there, and the amount that I'm catching the bucket, that's grays.
Yeah, but the next thing I want to say is that you're at the beach, your skin is bare, it is hitting you, and we know how many are hitting you,
right,
and how fast, and how much. That's grays.
And not how many are hitting you, is how many I'm catching.
How many hitting?
Right.
But the thing is, these things are hot, and they're burning you, and they're damaging your body.
Right.
So the damage to your body is
sieverts.
So sievert is the measure of health effect, detriment to your health.
Sievert, yes, the sieverts is an attempt to characterize how much health effect the radiation will have. So at one time, a few decades ago, we used what we call the Q factor. And the Q factor for quality, we discounted lower energy radiation, assuming that it's like using a small caliber bullet versus a large caliber bullet. The bigger bullet's going to do more damage, or the higher energy is going to cause more damage in your body. But in the recent decades, we've adjusted that factor for all non-alpha radiation to be 1. And the kind of thinking for that is that it doesn't matter if a 22 caliber bullet goes to your heart or a 50 caliber bullet goes to your heart. One of them makes a small hole and makes a big hole, but you still have 1 death. So currently, the way we factor the damage of different types of radiation, different energies, is that all beta and all gamma radiation has a Q factor of 1, so we just count it equally. And alpha radiation has a factor of 20, because alpha radiation has so much mass, and we assume that when it hits, it bounces off and damages 20 molecules or 20 cells, before it's been pelted.
So anyway, the thing that a very important thing to keep in mind is that, sieverts is a measure of dose.
Yes, sieverts is a measure of dose,
and it can't really be measured directly. It has to be estimated. It requires a conversion from grays, from other aspects of radiation?
Actually, that's equivalent dose. Grays is the dose.
Well, yes, but anyway, it is a measure of dose, is what I want to say. And grays, however, is much more of a physical measurement. As is
Irrespective
vectors.
of what a rabbit and a tree and a rock can all absorb radiation, and we can measure it in grays.
Right.
Okay, but the rock, we wouldn't think about it sieverts because there's no way you can affect the health or life of the rock because it's not alive. So sieverts tries to characterize what the eventual health effects will be, making things even.
Yeah, and so it's a little confusing because you'll often see people measuring, radiation, ambient radiation in the air in a certain zone, and they'll say, oh, this is, 0.1 microsieverts per hour. Well, that means they're trying to say this would be the effect on a person.
If this field were uniform, and if a person were in it, and they were subjected to this radiation, that they would get this many sieverts. So
it's actually confusing and possibly incorrect to use grays or to use some other measure would be better. And because we're not giving enough time. In our current environment, when we are looking at doses to people, it's usually measured in microsieverts per hour. It's in the level of microsieverts. And then in the case of, and that often works up to some amount of millisieverts per year.
Right.
And we could talk about these things, what's normal, what's standard, but it's in this range, this sort of magnitude.
Actually, the dose rates for most of Japan are in the fractions of a microsievert per hour.
Right.
So
0.
for a while we talked about 100 or 150 nanosieverts per hour, but the nano micro confused too many people, so we've standardized on doing everything rates in microsieverts per hour,
So
even though it's only 0.1
around
or 0.2.
0.1 is pretty normal for a lot of the world. Yeah, question?
Yeah, I was going to ask, is there still radiation from Long Island that you all can detect?
From Long Island? You mean?
There's radiation in Long Island, certainly.
Do you mean from 3 Mile Island?
Yeah, 3 Mile Island.
I haven't followed that.
No,
I don't think there would be much.
We can't detect the radiation from Long Island.
If you go to the parts of Europe and other parts of the world, you can certainly detect from Chernobyl, and certainly close to Chernobyl is quite a lot.
Because I couldn't remember if Long Island.
3 Mile Island.
3 Mile Island was before or after.
It was in the
before.
70s,
Yeah.
but it was before Chernobyl.
So
The amount of radiation from 3 Mile Island was not really easily detectable, even at the time of the accident, at any distance from the plant. Most of the effluent, most of the stuff that got out of 3 Mile Island were the things like the xenon and things that didn't stick around. So it made it very difficult for the people who were trying to blame the loss of value of their property near the plant on it, because it was hard for them to get proof that there was a direct effect. Most of the things that came out of Chernobyl and Fukushima, the cesium, the strontium, and stuff, didn't get out of the buildings. It stayed inside the plant, inside the reactor vessel. The more volatile ones, there was xenon, there was tritium, a couple of things like that, but nothing that caused a widespread contamination.
Was there like a difference in the way the plants were built?
There were small differences. There were big differences between 3 Mile Island and Chernobyl. The 3 Mile Island plant is very similar physically or theoretically to like Fukushima. The difference for Chernobyl used a very different reactor type. It had a graphite moderated reactor, so the thing that slowed down the neutrons to make the reaction more thorough was graphite, which is a form of carbon. And that's important because what happened at Chernobyl was it caught fire. And the graphite burning created a huge thermal plume which lifted the particles and the debris from the reactor into the air and spread it around as smoke and ash. Okay, whereas the accident at Fukushima, the moderator being water, the cooling being water, the materials of the reactor itself being steel and zirconium and concrete and iron, didn't have the ability to make chemical fire that could lift things, and spread things in the air the same. So the amount and types of things that spread and the way they spread was very different.
Yeah. So we can talk more about the levels that we're seeing. Of course, we'll start measuring next week. We'll start to build Big Igi Nano like this. Next week. And no, it's the week after next. Next week is GIS, and Taichi will be explaining that, and in a different room. And then the week after that, we have our first building session, and we will have 3 of those. We have scheduled 3. We'll probably get finished by the second one. And then you can start to measure and get a realistic idea of what are the levels, what is the range of radiation that we're finding. Later, we'll talk more about issues of food and environment, and we'll discuss a little more about, well, how many becquerels per kilogram is normal? What are the standards? What are the implications? What's being found in food? We can discuss this as well. So it's important to sort of get the range to understand the units being used and what the ranges are. Okay, 50%. I'm going to take a photo of that before we go. So any more questions? Because we have like 10 more minutes.
They didn't ask the obvious question, the question most people ask.
What's that?
How much is safe?
Well, that's what
Let's just say.
There
we go.
Right.
It's difficult to say because
How many times can you be stabbed with an ice pick and be okay?
If you're stabbed many times in the arm, only artery.
It's sort of the same
I
thing.
imagine you
yeah,
can-
yeah.
It's sort of the same thing.
So there's a little bit of controversy about that, but the
ice pick
no.
Because if you get stabbed once in the heart,
Yeah, exactly. One ionization event in DNA in a critical structure of your body that turns cancerous can end your life. Okay, but the number of interactions we have are in the millions. The number of those that aren't corrected by the body are in smaller numbers. So it really becomes an odds thing, and we're not really sure about how much of that is true.
would you regret it on Russian roulette?
Yes, it's Russian roulette where you have 100 million facing the cylinder and only one bullet. But the trouble is that when you walk out in the radiation, you're getting really millions of interactions per day.
Right.
So
yeah, we didn't even explain. Your body is full of radioactive material all the time, particularly
that's
radioactive
important.
potassium.
I said that K40.
And we have about 3,500 to about 4,000
That's in Asia.
becquerels.
I usually use 5,000 is the upper limit for maybe for Americans.
But anyway, you have quite a lot of this.
Well, it's about
Potassium.
100 becquerels per kilogram.
Quite a lot of this in your body. Quite a lot of radioactive potassium and other radionuclides in your body all the time.
It's way less.
Yeah, and this is in most of the things we eat. And we also have polonium-210 quite a lot in our food, and we have a lot in our body. So we're constantly being bombarded with this stuff. So
Carbon.
Carbon, yes, 14. And so we have a lot already, so it's hard to say, well, how much more is going to be enough to tip the scales and give you cancer and make you die? And it's all probabilistic. It's all statistical.
Would you say, this might be a silly question, but like somebody who's sitting too close to the TV or computer, they say damages their eyes, is that from the radiation?
No.
too?
No, it's not from radiation. Sitting too close. If there is an effect, and this is controversial actually, it has to do with the fact that you're focusing close to things and that you're straining your muscles and it pulls on your lens and that the muscles become fatigued. And it's like if you stretch a lot, you become more flexible. Well, if you tighten your muscles and hold your arm like this a lot, it's going to be pretty soon. It's going to be hard to make your arm go straight because you're staying in that position all the time. So looking at a screen up close is just pulling the muscles to a close focus. If you do that enough of the time, you lose the ability to focus farther away. And people naturally get that way as they get older anyway, because our muscles lose tone, the ones in our eyes become weak. And a modern computer with an LCD or even LED display, the radiation it gives off is light, visible light. We need that to be able to see. It is not in the ionizing spectrum. It doesn't have any effect on our bodies. Even CRTs, which we used for quite a few decades until maybe 10 years ago, the radiation that they gave off a lot more radiation. They gave off light from the phosphors, but that light was generated by accelerating the electron being very very high speed into the phosphor, would glow, and that caused also X-rays to be generated. So CRTs generated a lot of X-rays, but that was recognized in the 1950s, and we modified the design of them to include leaded glass in the front. That's why televisions had such a large, thick glass in the front, to make it very difficult to break, and also so that we could get enough lead in front of it to stop the X-rays.
Yeah. Any other questions? We covered a lot today. And again, you know, you have the list of words. You can Google that. There's other videos and stuff, and Wikipedia, and lots of places.
And we'll be back.
Storing radioactive material underground is a really bad idea.
That's a too general subject, because what's the material? And where is the underground storage? If we're going to store plutonium that way, well, what's the hazard of plutonium? Well, one thing, plutonium is wildly toxic. So you put it underground and you just sort of like pile it up in a cave, and that cave is wet and it drips and it you know, etches some of the plutonium off, and it gets in the ground, it gets in the water, winds up in the drinking supply. People are going to be poisoned by it. Okay? If you put it underground, well, not very far underground, and you just leave it in an open cave, well, some nasty people may walk in and steal it and make something nasty out of it. So just saying putting it underground, that's not enough of a description. And the solution for materials like spent fuel, which is a mixture of a lot of different chemicals that have a wide number of hazards. It's like saying, well, should you store things under your kitchen sink? Well, all kinds of things. Well, cleaners. What about, you know, poison? What about, I don't know, bread? Well, you probably don't want to store the bread and the rat poison together.
Yeah.
Okay, but there's no, that's a very general question that's difficult to answer. We can talk about it. You can go a whole hour just talking about the ramifications of what we call the back end of the nuclear fuel cycle. Is what do we do with the stuff that we take out of the reactor when we're done with it? And should we reprocess it? Should we not? And in some ways, it's like recycling. The uranium actually doesn't get very used up in a power reactor. Most of it is still there. So you could put it back into the process where we process the uranium ore and make more fuel out of it. But there's so much nasty stuff in it that it's more expensive and more dangerous than just digging up new uranium. And so we always start with fresh uranium to make fresh fuel. And so this stuff builds up. What do we do with it? It's dangerous chemically. It's dangerous. How do you store it? And that's why it's all been being kept at the nuclear power plants, because when nuclear power was envisioned back in the 50s and 60s, they had an idea what they were going to do with it. Well, if temporarily you store it in a pool at the reactor, you know, maybe 20 years, so it cools off and it becomes more safe, and then we'll process it and do something else with it. Well, in that time, the answers that they expected to come up with became politically unacceptable to people. And so the utilities just said, okay, we'll just keep it here until you figure it out. Consequently, in the last 50 years or so, in the US at least, all of the spent fuel that ever came out of a reactor is still at the reactor.
That's kind of crazy.
Yep. That's actually very irresponsible, because that's like keeping the bread and the rat poison on the table because you can't decide which cover to put it in.
Well, to me, like, if you ever have like a reactor go up and all the other radioactive materials is the same, you're going to either triple or quadruple.
Well, this was a risk at Fukushima, because
it was a worry.
They have this, well, a worry, because they have the spent fuel pools in the reactor buildings, one, and their cooling was compromised or damaged. And then you have this big storage, temporary storage for spent fuel that has a lot more. And that also needed power, and its cooling was damaged. So if that all had really been unable to restore the cooling, it could have been a really huge problem.
And most people don't realize that fresh power fuel is quite benign. You can hold fresh pellets.
Yes, you can hold it.
You can hold fresh pellets in your hand. They're not very radioactive. They're uranium, and uranium is not very, has a very long half-life, so it's very stable. It's after you put it in the reactor and break it up, the things that it creates all these other wild witch's brew of isotopes that contains things, some of which are very toxic, some of which are very radioactive, some of which are chemically problematic. It's interesting.
So, is that a good place to stop?
I think so.
I think so. And maybe we can stop the video now.
What time's the class was running? 6:20.
6:20.
You think cold fusion is a good way to go?
Cold fusion would be wonderful.